Hello everyone, I am Romit Kaware. Welcome back to the series on sediment management. In this submodule, we will understand the concept of sediment classification, try to understand its criticality in the total domain of sediment management. We will start with building an intuition as to what is sediment classification. Then we'll cover what is the current state of the art of doing the sediment classification. So basically, what are the conventional and the modern methods that are in use today. So let's begin. So first, we must understand what sediment classification is. Sediment classification basically translates to determining the sediment composition of a seabed or a riverbed. The sediment classification connects the various sedimentological details with the acoustic features to determine the seafloor types from the various measurements. It basically utilizes the acoustic responses of the seabed along with bathymetry and also sometimes focusing on the various attributes like the roughness, the texture of the seabed. So the primary goal here is to categorize and label the various measured seabed features. The acoustic response becomes a parameter in the classification algorithm, which aids in identifying the seabed composition and the associated seabed properties. In fact, the complex nature of the seabed is a consequence of an array of processes which has occurred over millions of years. The recreational, economic, military, and the oceanic applications require the qualities of the seabed. Thus, locating the stable environments and ensuring the proper operation of structures, pipelines, and the construction projects on the ocean seafloors require extensive knowledge of the strength, the hydraulic, thermal, acoustic, and seismic properties of the sediment. Moreover, different marine environments are usually characterized by the different sediment types. Thus, the sediment texture influences many biotic and abiotic aspects in the marine environment. The global ocean seabed structure is also influenced by plate tectonics, characterized by deep plains and mid-ocean ridges formed through the seafloor spreading. Now, these ridges slightly elevate the seabed as compared to the surrounding plain. Sediment composition varies from eroded land materials, biological decomposition, the various chemical reactions, and even extraterrestrial sources. Understanding bathymetry in this context is crucial for comprehending the various geological and oceanographic processes. High resolution bathymetric data also finds its applications in habitat mapping and hydrographic charting, which is crucial for the political and commercial interests. So, sediment classification plays a crucial role in determining the various engineering characteristics of marine sediments based on the interactions and interrelationships among the various sediment. The fundamental engineering properties like the bulk density, water content, permeability, and shear strength are all influenced by the sediment composition. In fact, when we consider the figure on the left, we see that the knowledge gap or the scientific gaps for the Indian Ocean, there are a lot of scientific gaps in this Indian Ocean region. Thus, if we need to consider the sediment classification, it can be based on the 2C to understand two share concept. In the 2C, it explores the concept necessity, emphasizing the importance of sediment classification, what are the various hardware to be used and how they may be deployed for the sediment classification. Then in the to understand, we talk about various techniques employed for sediment classification, providing insights into the various conventional and modern methods. Finally, the two-share section focuses on the various stakeholders benefiting from the sediment classification and also shedding light on the diverse individuals and groups which have a vested interest in the outcomes of the classification studies. Through this framework, a particular research can examine and communicate the significance of sediment classification. Now, when we come to the determination of sediment classification, how various sediment classification methods are there. Conventionally, these have been done on the through the in situ sampling methods like the grabs, excavators, samplers, videography, underwater photography, and various trawls. The classification outcomes heavily rely on the subjective visual interpretation in case of the optical surveys or the photographic surveys, which typically utilize the regional grid sampling. These methods provide researchers with an intuitive means to identify the bottom sediment type. So typically, these grab samplers and corals are utilized to extract the seabed cores, gravity corals or the vibratory corals, and the piston corals and are the commonly employed in investigations to achieve sufficient sampling depth and retrieve the intact sediments for laboratory testing. Now, different samplers have been developed for diverse requirements for the deployment platforms, with some needing high capacity lift winches and vertical lift for manipulation on deck. Now, on these undisturbed samples, a lot of geotechnical investigations occurs, which we will understand in the next submodule. Now, this is how a typical borehole data would look like in case of any borer or something. These conventional methods for seabed mapping have a lot of limitations, such as restricted number of samples, which makes them unsuitable for large-scale mapping. Now, despite the intuitive sediment judgments, these suffer a low efficiency, limited sampling, high operating cost, and restrictions in deep water sampling. Thus, the introduction of acoustic sounding technology has addressed these issues, which has enabled the gathering of bathymetry, topography, and sediment bearing pressure and other geotechnical parameters without actually physically going out there and doing sample collection. Modern subsurface remote sensing systems utilize various sensors to monitor the seafloor properties and have significantly reduced the capital and time constraints. So this is how a acoustic system would work. The most common would work consists of a pinger or an acoustic beacon that would emit a regularly timed sound pulse. This would be directed towards the seabed. Seabed would then, based on its texture would and its composition, would reflect it, and it's detected by the surface vessel. The ping also travels directly back to the surface vessel, and the distance from the pinger to the seabed is also calculated by measuring the time difference between the direct ping and its echo, and then using this scattering phenomena, the sediment classification, the composition is all found out. In fact, various kinds of sonars have been developed, and this figure shows there are a lot of, it shows a schematic of the various data coverages that are there with the different sonar systems. So high frequency active sonars operate around 30 to 500 kilohertz. There are also systems which allow increasingly greater resolution as the frequency increases, but at the expense of the range. So various types of sonars have been developed based on their frequency ranges, the beam patterns, and many other aspects. The multi-beam echo sounder are widely recognized for measuring the bathymetry in the various water bodies. The backscatter data obtained from these multi-beam echo sounders provide insights into the physical properties of the seafloors. The major benefit is being the cost-effective high spatial coverage. Then there are also echo sounders, which are the most straightforward acoustic systems which utilize a single beam towards the ship's nadir and typically employ low frequency signals which are less than 20 kilohertz. Side scan sonars are another type of acoustic systems which provide extensive seabed coverage, which spans a few hundred meters to over 60 kilometers, and is achieved by emitting two broad beams on the each side. They can also acquire bathymetry and can achieve resolutions ranging from 60 meter down to 1 centimeter by utilizing the various different frequencies. Thus, the use of the active sonar systems, which are basically the sonar for characterization of the seafloor bathymetry and topography, has been since the last 3 decades, primarily in the form of the multiple micro sounder side scan sonars or the acoustic ground systems. These can measure the size of objects to meter resolution level along with their depth and hardness to transmitting and receiving sound pulses. These can be then mounted on the various vehicles, like there are remotely operated vehicles and the aerial underwater autonomous underwater vehicles. So the ROVs are unmanned vehicles that have operators on the surface control, while the AUVs operate autonomously and are pre-programmed to follow a specific path. There are also various video and photographic surveys that can be conducted using cameras mounted on them or by divers using the underwater cameras. There is also an urgent need for large-scale spatial data on the various underwater species, the communities, and the bathymetric data in all, which has resulted in the application of distributed modeling. This has enabled the employment of full spatial coverage data of the various environmental variables to predict the various distribution patterns. Now, these images show the various aerial surveys that can be conducted. Topographical features, donation, and seaweed biomass can all be calculated using various models as well. The digital elevation model can also be used to derive bathymetry in this case. As mentioned earlier, the various vehicles such as ships, submarine stored systems, and ROVs, AUVs can be used to deploy the various acoustic sensors. Although ROVs are complex and expensive, they offer direct control and capability to image extensive areas of the deep seafloor with high positioning accuracy. But there are logical constraints such as dive and ship time availability, often limiting the spatial scope of these surveys. AUV are also there, and the AUV collected data guide the subsequent ROV deployments with high resolution imaging. Thus, developing a sizable acoustic aperture is necessary, but again, it may lead to trade-off between imaging distance, resolution, operating frequency, and the aperture sizes. Again, we can similarly see there are various feature mapping techniques like the optical surveys and the aerial ones. Thus, the way forward would be developing the hardware capacity, that is the acoustic capacity and capability. This can be done by outreach, engage, and sustain, which is the major part of the UDA framework. That's by developing various center of excellences for the skilling of workforce. We can develop an ecosystem for the development of homegrown acoustic systems catered to the specific tropical conditions. With this quote, I'll end my discussion. Yeah. Thank you, everyone.